x n. Gotta freak out.
Oh, that's pretty cool.
Yeah, and then 1 minus n. Notice how the first numbers are 2. It's not really going to affect much, but you can, if needed, adjust the starting number up here at the very top. So here it starts with a 1. If I want to start with 2, I could put a 2 there, and that would be the starting number. And oh, there she is, right there. So we're looking, what's our answer? Converge, yay or nay?
Yes.
Yeah, what does it converge to? Yes. So it converges to a value of -2. That's adequate. All right. This is no sum. That was simply sequence convergence. Let's see. Series means sum. All right. Use the nth term test to determine if the series diverges. What is the nth term test? I forgot. It's supposed to be n equals 1. I don't know why it says negative. Nth term test is basically graph the thing and look at what the sequence does. Man, check that out. Zigzag, zigzag, zigzag. And now it's bouncing back and forth. I mean, what do we think here? It's going to be in dots because it's plotting points. So the nth term test, you're looking at what is the sequence doing as n approaches infinity? What is it doing?
Point 0, 0, 0, and point or negative 0.0.
Yeah, but the further you drag that slider, the closer it's going to be getting to what's in the middle of there, which is 0. Technically never will, but a limit is not necessarily telling you what it equals. What is it approaching? So as I go farther and farther to the right, this graph is approaching 0, so I'll just say equals 0. Now, this, as being the nth term test, that means test fails, which means I don't know if the series converges or diverges. We actually have to look. So we need to look at the graph on Desmos because right now we got no other tools. So I don't look at my series graph or my sequence graph. I turn on my sequence of partial sums and I look and see what's up there. All right, well, this one's bottoming, flattening out. You know, what do we say? Do we say it converges? Yeah, we say it converges. So according to the graph, we see it converges, and it's converging to a sum. We'll say approximately, let's go 1.073. I mean, I'm at term number 480. You could drag it farther to 1,000. Sometimes it'll blow your Chromebook up. And I just get you close. Let's see. Let's skip that one. Here's one like what we did yesterday. Determine the sum of the geometric series. Now, I mean, technically, it's a negative thing again. It didn't make an equal sign. I guess technically, you could just check your answer with Desmos. But we learned that for an infinite sum yesterday for a geometric series, if we know what the value of R is relative to 1, the absolute value of R is, we can tell you if the series will converge or not, and we can find the true sum without approximating. The only thing is that the series has to be written in the form of A1 times R to the something power. So I need to do a little bit of work. So I'm going to take our form of this, and I'm going to do some rearranging. So I'm going to write that as 3 to the negative n minus 2 power times 2 to the n plus 1. And then I'm going to ship that 3 to the denominator. It becomes 3 to the n minus 2. And now we just want to see 2 to the n and 3 to the n. So that means we have 2 to the 1 times 2 to the n over 3 to the negative 2 power times 3 to the n. Which means if I move that 3 to the negative 2 to the top, that's 9 times 2 makes 18. We got 18 times 2 to the n over 3 to the n power. So we rearrange our explicit form to be 18 times 2 over 3 to the n. Well, 2/3 is r. So the absolute value of 2/3 is less than 1, which according to the geometric series test, it will converge. The series will, the infinite series. It's a G. It converges to a value equivalent to A1 over 1 minus R for the sum. Well, R being 2/3, I got 1 minus 2/3 in the bottom. A1 would be the value if I put 1 in for n. So that's what? 18 times 2/3. 18 divided by 3 is 6, times 2 is 12. And that would give me my sum. Is that 12 divided by 1/3, 36? Makes it by hand. That's what we would do. We hopefully, let's confirm that with Desmos land here. Pain in the neck, type some of this stuff in. Yeah, it's regular. I screwed up my equal sign. That's a regular 36. Negative n plus 2 times 2 to the n plus uno. And of course, I don't see anything because I got to get to where I can see 36. And then I see the hook. And after 480 terms, it approximated a sum of 36. So confirmed our work there. Depends on what the directions say. If it says show all work leading to the answer, then I would say please. All right. Determine the sum of the telescoping series. All right. Telescoping series. That's supposed to be equals 1 again. Good night. All right. So there is no formula for the telescoping series. What you do is you start expanding it. I'm trying to do this by hand, and we see if eventually a term will collapse. So I'm going to start writing out terms. I'm going to begin by putting in 1 for n. That gives us 1 minus a fourth. Plus, put in 2 for n. That gives us a half minus a fifth. All right, so far we're 0 for 2. We're just going to keep trucking. Put in 3 for the n. We got 1/3 minus 1/6. 0 for 3 in terms of stuff canceling. All right, I'm not giving up yet because eventually, because I know that something should eventually cancel because I have a number minus another number, and I'm starting to see that there's playing out a pattern here. And then plus, put in 4. Hopefully we get something to cancel this time. 1/4, there's the first cancellation, minus 1 over 7. All right, so 1/4 is the first thing that cancel. I got to keep going until I get 2 things to cancel in the same set of parentheses. So we can put 5 in. 1/5 minus 1 over 8. All right, well, 1/5 cancel. All right, well, at least we're getting somewhere. Put in 6. 1/6 minus 1/9. The 1/6 cancels. All right, well, so far what I need to happen hasn't happened yet. Please happen on this one because we're all running out of room. Put in 7. There it is. 1/7 minus 1/10. 1/7 will cancel right there. There's the term that collapsed. First and last canceled. So what that means is the sum of this telescoping series should add up, the infinite sum, to be the terms in front of that collapsed term that weren't canceled out. So 1 plus 1/2 plus 1/3. What's that? 1 and 5, 6. So 11/6. And then you could confirm that with Desmos, but I'm not going to do that right now. Did I add wrong? You just told me to wait, to wait.
No, look at the problem.
Can I unfreeze? Okay. I mean, you told me to wait, so it was on hold. All right. My computer's starting to bog. All right. Now, you will see why in a minute. All right. We can go look at another kind of series real quick called a p-series. We've encountered some of these already, where a p-series is simply something that I'm trying to find the sum of, an infinite sum, and it can be written in the form of 1 or a number other than 1, that part doesn't matter, over n raised to an exponent. So n to the p power, hence the p series part. So p series will converge if and only if the exponent here is less than, or sorry, converge if and only if the value of p is greater than 1 when it's written in this form. If it's less than or equal to, series diverges every time. And we're going to see that with a couple of examples. So let's do, let me see. Let's do the top one, and we'll do top one and the bottom one. So the end goal here is to look at a series and be able to term, does it converge or not? We have some steps that we have to hit along the way. So let's start here. Given this series, this is called a harmonic series, 1 over n. What is the result of the nth term test? Right, well, nth term test basically says evaluate the limit of the sequence, not the series, as n approaches infinity. Turn off my partial sums, graph my sequence. Let's see what's up. Where are you at? There you are. So what I do is I write the result of the nth term test, which is the limit as n approaches infinity. A of n is what's on the inside here, is equal to 0. Since it equals to 0, the test fails. If it did not equal 0, that means it diverges, which is the one that honestly you root for because that means there is no sum. All right, so the test fails. Now it says write out the first 4 partial sums. Ooh, all right, this is where I'm a little bit of a prick, but it's not that bad with Desmos. So what we do is this. First 4 partial sums. Let's turn on our partial sums. Turn this off. Let's go get their values. Yeah, click the first 4 dots. 1, 2, 3, 4. So my first partial sum. Now we know what the value is here. So I'm going to write their sums first. Scroll what?
Scroll up one bit.
Do you got a 1 here at the top?
Yeah.
Do you have 1 over capital N?
Well,
When you do the solution thing,
You got to use the sequence of partial sums. All right, 1.833. And then the fourth partial sum is equal to 2.083. Now, those are the values of what? What did partial sums mean? Like, what do these numbers mean? Other than the first 4 dots that I clicked on the red thing.
the first four value the sequence of it.
No,
that's the first, all of them I added up.
that's right.
Yeah.
So first partial sum is the first term. Second partial sum is the sum of the first plus the second term. Third partial sum, add up the first 3 terms and so forth. And that's what they mean. I should just keep that part in mind. All right. So
I guess that's why we get like solution from for that one.
Yep. So graphically, does the sequence of partial sums converge? Well, when in doubt, look at some more terms.
My 700 is still running.
So
Still
still rising. So we're going to say what? Diverges. So if it diverges, that means at the very end there is no sum.
No sum.
Now, result of the p-series test.
Oh, and then how can we fill the nth term test?
The nth term test was, we said the test fails because it's inconclusive.
Oh,
But basically, if the nth term test fails, it could technically still diverge as a series. All right, the p-series test, which is what we're looking at and we're trying to learn today. Now, our explicit equation was 1 over n. Now, p-series are when you have 1 over n to the p power. Well, for our problem being 1 over n, p is equal to 1. In order for a series to converge, the exponent has to be greater than 1. Well, since our p was not greater than 1, so since it equaled 1, the series diverges by, and then if you're using a test to classify this, you write the test and I just abbreviate PST, like I do for geometric series test.
But all we're doing is figuring out see if it converges.
Error converges. And if it converges, we guesstimate a sum. All right.
So what's the point of the p-series?
P-series test is a way for you to look at an equation like this one and know if it converges without having to look at its graph. It's something that a lot of time and effort is spent in doing it by hand in a Calculus 2 course. Well, I'm just showing you how we can just analyze it graphically and save all that for if or when you have to take that. All right, skip the one in the middle. Now, basically, if I had to do one like it was in the middle, what I would do, we're not going to do it right now for the sake of time, is remember that n to the negative 4 power could be written as 1 over n to the 4th. What's the value of p for that one? P is 4, so would the series converge or diverge? Converge by the p-series test. And to estimate the sum, I would just look at its graph. All right, let's look at this one. Let's go through the whole kit and caboodle here. So, yeah, nth term test result first. So, Eustace must tell me that's a of n. What is the limit as n approaches infinity of a of n equal to? So, oh, you got to be crazy. All right. Oh, it's the shorthand for cubed root, but there's a button for it somewhere. Miscellaneous, right there. Slap a 3 in the corner. Put my ends in place. Right. And turn off partial sum because it's not what the end term test deals with. Turn on my mixed sequence. And I look at it, and our favorite thing in the world happens. This equals 0, which means that the nth term test is useless. Doesn't tell me anything. Means I got to do further investigation. So the next block was first 4 partial sums. I'm just not going back up. So first, second, third, fourth partial sums. Last semester I made them write it out and add it all together, but just write the sums here. All right, so click and look, turn on our sequence of partial sums. 2, 3, 4. Of course, they're stacked on top where I can't do it like that. First partial sum is 1. Second partial sum, 1.63. Third partial sum, if I had all 3 numbers, would add up to be about 2.111. And fourth partial sum would be about 2.508. All right. Third blockaroo. Does the graph of the series converge? I got a head nod by Spanky.
No. It diverged that way.
Really? Huh. Diverges,
God.
which means that there's no sum. So estimation of sum on the very end would be no sum. Now, what about the p-series test? It's not useless because we could have figured that out right out of the gate. So our explicit formula is the cubed root of n over n. Well, I could use some properties of exponents here and write it as a p-series. Yeah, the cubed root is n to the 1/3 over n, and when you divide like bases, you subtract those exponents. So I could write this as 1 over n to the 2/3 power. Looking at that exponent, in our case, this is a p-series. P is equal to 2/3. Well, since 2/3 is not greater than 1, it diverges. So I could have already known that without having to look at the graphs. It diverges by p-series test because 2/3 is not bigger than 1. Yeah. Now we got the last kind of series that we're looking at, and words of wisdom. All right, there's a new thing for Desmos that we need to use for this. It is going to bog your computer down. So if you got a lot of tabs or things open, like I just opened it up a minute ago on mine, and it sounded like I turned on the air conditioning on my computer.
Really not.
It's well, if you got like 35 Google Chrome tabs open, you better shut them except for 2. I know, and the other thing is Google Meet's a freaking memory hog too, but we'll do the best I can here. All right, we got to talk a little bit about what the heck a power series representation is before we get into using the applet. So basically, a power series is when we're looking at, if you remember, the geometric series test, the summation of anything that can be written as a geometric series, some number times r to the n power, we could determine the sum, which came out to be the first term over 1 minus r. What the power series does, it kind of works backwards a little bit. So if I have this summation of something to the n power, we know that it equals this sum. And I could theoretically expand my terms out to rewrite a power series like this. So the summation of an infinite number of terms to be approximated by some polynomial. And it's something else that is a lot of time, and there's a whole chapter that deals with this in a Calculus 2 course. Usually it's something that a lot of people don't understand. So my only mission in life is to expose you to it. So if you ever have to take it, you can say, I did kind of see something like this before. And they're going to use some actual calculus stuff to do what we're doing. But we're going to look at it graphically. All right, so let's talk about strategy here. And I know right now we're like, still don't know what this thing is. Let's look at this first example. I'm given a function, f of x. F of x is equal to 2 over 1 plus x. And we're like, well, what is going on here? What we're trying to do is we're trying to take an equation like f, and we're trying to rewrite it in the form of a power series. That's what I'm trying to write in the form of a power series. Well, in order to do that, this equation that you're given has to look to be in the form of a1 over 1 minus r. It's got to look in that form. Because if it looks in that form, then I can reverse engineer a summation. Our issue is it's close to being in that form, but not really. We have 2 over 1 plus x. If we rewrite this as 2 over 1 minus negative x, then I can identify what everything is. Where 2 is a1, r is negative x. Bingo. All right, so expanded power series. Well, technically, we haven't really. I should have put the other one first. I should have put the third one in front of this one. So remember, if we know that some summation is equal to a1 over 1 minus r, technically that is also equal to the summation of an infinite number of terms. I could start with n is equal to 0 to infinity of a1 times r to the n power. Well, the 2 over 1 plus x is the sum. That's what I want it to add up to be. So my power series, if I know a1 and I know r, using sigma, is going to be equal to the summation from n is equal to 0 to infinity of a1, which is 2, times r, which is negative x, raised to the n power. Simple enough. Like, okay, sweet. Well, if I know that's the power series, find the first 4 terms. It says non-zero terms because language is used in calculus too, but we're not going to encounter one where we have 0, I don't think. So write out the first 4 terms. Well, my first term is going to be when n is what? Don't fall for it. This is your first term. So when n is 0, I put 0 in, my first term is 2. And I got plus. That's my first term. Now I put in 1 for n. I put in 1 for n. I got negative 2x. I'm going to write minus 2x. So that was, for us, was n is 0. Then we got n is 1. We're going n is 2. And then n is 3. That'd be my first 4 terms. All right, so now I put in 2 for n. Well, 2 times negative x squared just makes plus 2x squared. Then I put in 3 for n, be 2 times negative x to the 3rd power. So that makes minus 2x to the 3rd. And then that's just going to continue on forever. So let's do this. If you got this little applet thing open, we're going to type in where f of x is. We're going to type in our 2 over 1 plus x. We're going to look at it. 2 over 1, come on, plus x. All right, power series. All right, so this first one here. All right, remember I said this thing's a memory hog? Like, look, it took my computer 5 seconds to make a change. Yeah, so you just got to give it a minute. All right, power series, the sigma, I need to put my equation in there. Now notice how it's using i's instead of n's. So it's just something you got to pay attention to. So our power series is 2 times negative x to the n. Well, so I can get rid of this 1 to the I here and call that 2. All right, and we got x should be negative x. Don't put it in parentheses. And then the I is representing the n. It's going to take a minute. Here's something we can do. I think if you make this number smaller, it'll hurt your computer's head less. Yeah, I know. It's going to take a minute. Right. So also, you just got to give, I'm telling you, this thing's going to bog the computer down. Also, our expanded power series, down here where it says power series expansion, let's write our first 4 terms. Notice how I got this turned off. I think yours is too momentarily. But we'll delete, and then we're going to type in 2 minus 2x plus 2x squared minus 2x to the 3rd power. It's just 2 parentheses negative x with I. All right. It's got I as an exponent. All right. So Chromebooks are taking a little while. Well, all the virtual people gave up on me and they left.
Did they really?
Yep. So
God bless.
I know, I'm right in the middle. All right. Notice how on my computer, your computer will eventually catch up. I went ahead and put the power series expansion down here at the bottom and it turned itself on, which is fine. Do you see how there's a curve here, which for me is in red? That is the summation function that it graphed. Our power series, which for me is in orange, notice how they kind of blend in and become the same curve in a certain area. We see that? The area where our power series is equal to or getting very close in value to the actual summation, that area where they look like they lay on top of each other, is called a radius of convergence. So we'd want to be able to determine, well, where are these values very, very close to one another? It's actually very easy to find. We look here, radius of convergence, interval of convergence, all the same thing. What has to happen for a geometric series to converge? According to the geometric series test, what has to happen? What has to be less than 1? Yeah, the absolute value of R has to be less than 1. Well, for our problem, what's R? R is negative x. So what we do is we're going to solve this here. The absolute value of negative x has to be less than 1. All right, well, that means that negative x be less than 1, or negative x has to be greater than negative 1. and I solve these two inequalities. So I divide both sides by negative, it flips the inequality sign. X has to be greater than 1 on one side, or X has to be less than positive 1 on the other. So my interval of convergence, I got to combine these things together. That's going to go from -1 to +1. You can write it as an interval. You write it as an inequality. I really don't care. So if we're looking in here, which is what I originally had, that's what these two lines are. These two lines here, you might be like, well, they really don't match that well inside from -1 to +1. You're like, okay, but if I added more terms in, which is going to hurt my computer's brain, and it might take it 10 minutes to graph more, or if I start putting more terms in my expansion, these two lines here are going to wind up matching very, very closely. It still hasn't done anything. Like, for instance, the next term would be plus 2x to the 4th. It might take it 5 days to adjust. And then the next one would be minus 2x to the 5th. Come on, baby. Get on there. I don't know how long we give it. Did I blink and it do something, or just I have not done nothing?
No, I think that's how it's supposed to be. Mine took like 3 seconds and went through 3 different changes.
No, she's frozen. But I just tried to turn it off and the graph stuck there. It takes it a minute because having to add all this. It's probably still trying to add.
Mine is like right now, and I just watched the change 3 times.
Oh, really?
Yeah.
So the Chromebook's faster than my book.
Yeah.
All right.
Watch if I add see, that's just 2x. If I add the power.
Check yours out. Oh, it did something.
That's 2x.
So maybe in 20 more seconds it'll flip and make the other one.
Changed twice.
Yeah. Yeah.
Yeah. So you see how slow this thing's going.
That's to the
But
2x.
yeah, the more terms you add in the expansion, the closer these two curves are going to match within that interval.
Yeah, mine doesn't need it.
The blue, like this here.
No, that line right there. How it goes up. Mine does. Mine goes.
This one.
Mine matches.
Okay, it's a good shot.
Which one is it? Which one is the blue one?
It's.
Oh, this here. Do you have negative x to the I in this?
I got it, but mine still don't match yours. Mine goes down and not up. Mine.
You got positive too?
Yeah, but it's like this. It's something different. See how it goes like. Oh, wait, now there it goes. Yours goes up. There it goes. Showing. I mean, my other stuff's loading, surely that's loaded now too.
I'm scared to zoom in.
Oh, God, I can't laugh.
Yeah, mine goes up. All right, I just want to do one more of these. They take a while, and then our computer's head's hurting. So which one to do next?
I'm gonna make that.
I mean, if you got it, go, man. Let's do the bottom one. See the bottom one here.
The one that's gonna produce the least.
Well, the one that would probably match something that I would make you do on your quiz or test. All right, so I want to do the whole power series expansion thing again here. In order to do that, this has got to be in the form of a number over 1 minus r. Well, I call it spot the knot. The main difference is this number must be a 1 before I get too far along. So the first adjustment that we're going to do is we're going to divide everything by 2. So that means I'm going to have 1/2 x squared over 1 plus 2x. I divided everything by 2 first. That gave me my 1. Now the next thing is I need to have a minus. So that's a minor adjustment there. You got 1/2 x squared over 1 minus negative 2x. Now that it's in that form, you can identify the first term. You can identify r. the first term in this expansion that we're going to make to represent this function is going to be 1/2 x squared. Now, I can only do these power series expansions for certain kinds of equations. I should have made that clear earlier, but they're going to kind of be these rational functions that look in this form. R is negative 2x. So I had to make sure I made the adjustment so that way the front number was a 1, and I needed to rewrite it so instead of a plus, we had a minus. That's how we get these two. So let's write our power series and then write out our first 4 terms. What is the power series going to be? The summation from n is equal to 0 to infinity of A1. I can't see it. What was that? 1/2 x squared?
You're in the wrong spot.
No. I don't think so.
If you're writing out the power series. Oh.
I'm writing the sigma part.
Sigma.
A1 times r to the n. What was r? Negative 2x. All right. So let's write out the first 4 terms, knowing that that's the series. So first term in our case is going to be when n is 0. So we're going n is 0, n is 1, n is 2, n is 3. If I put 0 in for n, I got 1/2 x squared. Put in 1 for n, 1/2 x squared times negative 2x. Is that negative x to the third? Put in 2 for n, 4x squared times 1/2 x squared, 2x to the 4th. And put in 3 for the n. Oops, trying to record myself talk apparently. 2, 4, negative 8 x cubed times that. Negative 4x to the 5th, yeah. And then that continues on. All right. Let's put this into Desmos, and then we'll try to figure out our interval of convergence. So that way we can give the Desmos brain time to figure out what in the world is we're trying to do to it. All right, so f of x was x squared. And down here we got 2 plus 4x. All right, our summation. One half x squared times negative 2x to the I. All right, so I got that. It'll take it a year to graph that. We'll come back to the convergence thing. Now we're going to put in the first 4 terms of our expansion. 1/2 x squared minus x to the 3rd plus 2x to the 4th minus 4x to the 5th. Actually doing something relatively quicker. All right.
All of this on one action behind this.
Yep. All right. So last thing that we want to do is to figure out, after this thing starts plotting, I guess, is inside of what interval will my power series expansion be very close to the actual function, which I can't really see colors here, but it would be red. Inside of what interval? To figure out your interval or radius of convergence, you're trying to figure out when the absolute value of r is less than 1, because that's what has to happen. Our r, what? Negative 2x? Yeah. All right. Is equal to negative 2x. So I'm going to say the absolute value of negative 2x has to be less than 1. So that means we saw negative 2x must be less than 1, and negative 2x must be greater than negative 1. Divide both sides by 2. X is greater than -1/2. X is smaller than +1/2. So our interval of convergence is in between negative and +1/2. So we'll make that adjustment into Desmos. I'm just going to go 0.5. And so as I start matching, or not matching, my power series, now I see that it's kind of starting to get separated here. The more terms in your expansion of your power series at the end, we only wrote 4, the tighter the fit, I should be able to get it to the actual curve inside of this radius here from negative to positive 0.5. I don't want to get too in depth because that's what calculus is 2 is for, but it ties in kind of a little bit what we're doing analysis wise. So that's as far as we're taking it. And that is the end of sequences and series. Horrible.